Guys, let us continue with our revision. Siphele yesterday, siphele question we are about to do question 3, yes. Question 3, question 3 on September 2021. Anna? Okay. Okay. Before we take a transformer, before we start doing question 3, I want us to go to as a reference. Let us go to 104 on our textbook. 104 on our textbook. Okay. And 6. Nimbonela na? Tano guys, they talk of Indoni transformer at what? At no load. Yeah? Okay. A transformer on no load draws a small amount of power. Yeah? Remember, Indoni, yesterday we covered Indoni open circuit what? Test. Basically, open circuit test is a transformer at no load. What are we trying to calculate, guys, when we are doing open circuit test? We are trying to calculate in one equal losses. So we are trying to calculate in one equal losses, which is equal losses in one the constant losses. Let's go to P naught. Okay. If we look at the schematic diagram or the equivalent circuit of a transformer on no load, you see that we don't have a secondary current. Why? Because the secondary side of the transformer is not connected to any load. The only thing we have there is induced EMF and terminal voltage, of which is we know at no load induced EMF here secondary is equals to a terminal voltage, because there is no internal voltage drop. Internal voltage drop equals current and what? And resistance, or a current and reactance, which is the reactance. A transformer is a inductive circuit. Okay, so asinayo a voltage drop, hence a induced EMF is equals to a terminal voltage. And also the power output of a transformer at no load to money goes zero. Makes sense, because we don't have any output. Yeah, okay. The only thing that is now is input power, which supplies ion losses. So, looking at a diagram, we see that the current coil there is the primary current, which is the no load current. Guys, this current is divided into two components because it is not in phase with the what? Voltage. Okay, it is basically lagging. If you look at the diagram, you see that R1 and X1, that represents a resistance of the winding. So guys, it represents the resistance, OR1 represents the resistance of this winding. And then OX1 represents the inductive reactance of this winding. Yabo? Okay, with transformer, you don't have any capacity because a transformer is made up of winding. It's, it's resistive and inductive. And okay, so the only current that is flowing is the primary no load current. Okay, this primary no load current has two components. One, IC, and one, IM. Of which is, guys, IC is responsible for supplying equal losses. And OIC is in phase with the applied voltage. If you look at the vector diagram, let us look at figure 3.3. The IC is in phase with the what? So if IC is in phase with everyone, basically, if you want to calculate that no load power, input power, it's V times money. IC makes sense, because V1, because IC, which supplies the core losses, is in phase with the supply voltage. Then out of phase with the supply voltage, in one, what you call magnetizing what current. This current is responsible for creating a primary magnetic field. Okay, if we see that, then I'm only gonna draw a voltage and current. Okay, there's a phasor diagram here. Okay, obviously now we are referencing to V. Okay, do you see that this is I naught? I naught is out of phase with the what? Supply voltage by a certain angle, which we call the no load phase angle. Okay, so basically, I naught has two components. There is the what? The let's call it there is the vertical component. The vertical component is money I am. Then the horizontal component is the one that is in phase, which we call it I what? IC. Okay. OIC, we calculate it as I what? Not cos, making sense, It's because, this is using trigonometry, to find OIC in terms of OI naught, Here's your reference angle. You want what? You want the adjacent side. So uzosebenza cos times what? The hypotenuse, Then OIM is equals to bani I naught. Okay. Let us go to the next page, page 106. Nancy, everything I was explaining, as one is the formulas. This is for a transformer on what? On no load, guys. For a transformer on no load. Let us look at the formula. Lane square root late I naught square root I m squared plus IC. This is basically using Pythagoras. Okay. That is basically using Pythagoras. And also you can also manipulate and get IC, which is P naught over P1. Okay. Now let us go to a transformer on what? On load, no? Can move on, no? Please, guys, those who are not here, cala ninjongele open circuit test, yabo? Because the open circuit test is based on a transformer on no load, yabo? Open circuit test helps you calculate iron losses, ne? Siyasenza yona izolo. It's not, after I've explained this, it's not really that difficult, yabo? Okay. Then what what do we do if we want to calculate and just to help those bebengekho yesterday? When we want to calculate copper losses, we do intoni? A short circuit test. Yabo? Okay. We do a short circuit test. Uh, Transformer on load. Okay, let us look at a transformer on load. Nah? Okay, basically when we have now a transformer and load, it means that we have basically connected a load. Nah? So we have we do have a output. Nah? We do have the output. We can no longer say the output power is 0. Yabo? Because now we have connected a load. Nah? And we cannot longer say that the back EMF is equals to the terminal voltage. Why can we not make that statement? Is because now we have current flowing in the secondary winding. Né? Now we have current flowing in the secondary circuit. Okay? Meaning which, if we have current flowing in the secondary circuit, we have internal what? A voltage drop due to the resistance, the reactance, and the impedance of the secondary winding. Anna? Okay, let me just read through. Anna? 80. When an electrical load is connected to the secondary winding, I2, current I2 immediately begins to flow through the winding. Anna? This secondary current is determined this secondary current is determined by the what? The characteristic of the load. The load that we connected. Yeah, okay, what do they mean by that? If, let me just draw the secondary. Okay. Just to show you an explanation there. Yeah, okay. Here is my load. ZL. And my load has a resistor and a what? An inductor. Okay, the load that is connected to the secondary side of the transformer. Meaning which, okay, if my load has a resistance, I'm expecting that a current I2 will lag, current I2 lag what? The terminal voltage. Anna? Okay, by a certain degree, not 90. Yeah, but it would be 90 if it was only my load was only inductive. And the load can be what? Can be a resistor and a what? A capacitor. And meaning which I2 will lead V2 by a certain angle. That is what they mean when they say this secondary current is determined by the characteristics of the what? Of the load. And the magnitude of this is influenced by the impedance. And the higher the impedance, the lower the what? The current. Okay? If the impedance of the load is high, a current is what? Low. This is what? Basically, Ohm's what? Ohm's law. Anna? Okay. Uh, then it stays there. I2 will either lag or lead voltage V2 depending on whether the load is what? Inductive or capacitive, which is what I've just explained. Anna? Okay. So we're almost there. We're almost there. Now we're gonna talk of equivalent resistance, equivalent reactance, and equivalent impedance. Because now we are dealing with a transformer on load, yeah, meaning we must consider all the voltage drops. We are no longer doing N3, N2, N4. Why? We didn't consider those N2, N3 because we are only dealing with an ideal transformer. We were dealing with a transformer whereby the input power is equal to the output power, which is practically speaking, there's no such a transformer due to voltage drops and losses. Okay. Guys, sometimes if you can just take a picture, I don't mind. Yeah, but taking picture with a cell phone is a quick way to grab a note. Yeah, but then yazazi uba uzophinda ubhale. Yeah, but what I want by attention, I don't mind can copy your phone, then you take picture of a note. Okay. So we're gonna look at equivalent resistance, yeah, equivalent reactance, and equivalent what? Impedance. So basically, guys, we want to uh, determine the internal voltage drops of a transformer, né? Okay, because the internal voltage drops, they determine our terminal voltage. Okay, in terminal voltage, guys, it's very critical. Yeah, hence, we will get to a point where we talk of a voltage regulation. Yeah, imagine uthi uplaga a cell phone yakho or you charge a phone on the socket outlet. Ithe ithathe. Why? Because maybe the transformer that is supplying these premises is having poor voltage regulation, meaning which ikhupha instead of getting what 230 volts, you wanna ikhupha bani 400 volts. I'm making an example. Yabo. So can plug a high charger yami izothini? Izotsha immediate because of poor voltage regulation of the municipal transformer. You see? So that is why we deal with a voltage regulation, yeah, of a transformer because into zethu zombane zisebenza at a certain amount of voltage. Yabo? Should we exceed a voltage, we burn our electrical appliances. Okay. So guys, you get where I'm going with this. Yeah, but if voltage regulation is important, because izinto that we use in electrical are designed to operate at a specific amount of voltage. Yeah, but if ungathatha i-dryer uyiconnecte in South Africa, standard voltage in South Africa is 230. Ne? So every product oyithenga e-South Africa isebenza ngombane operate ngalaban, 230. But the standard voltage in America is around 110 volts. That is their own regulations. That is what they feel, Bona, as Americans. It is a safe voltage to use ending. Yabo. If one tire will head dryer from South Africa, you take it, you connect a way socket outlet, just America. It won't work. Why? Because the voltage is small. Yabo. Their supply transformer is giving what? 110 volts. And if it's a transformer, a kamasipala that has poor voltage regulation, meaning if either the voltage is higher than the 230 or it's lower than the 230, then we're gonna have problems only. Okay, that is why it is critical to maintain a voltage, to regulate it. Output copper layer. Because what will happen if baninzi abantu like lendez nyoga, if baninzi abantu connected la transformer is secondary side could draw more current. More current means more internal what? Voltage drop. So output a transformer, it no longer supplying us with 230, but it's supplying us with a lower voltage. Hence we say we say the transformer is what? Overloaded. Okay. No, izoenda apha ke ngokwesini isitsha yabo. But their circuit breakers and protection system as a detector loo nto uba ingatshi itransformer yethu, instead bayithini itrip once i-current exceed a certain amount of value. You will learn more about the circuit breakers. Yeah. Okay, they are used for protection. So guys, let us look at this. So basically it's to do a transformer calculation. We'll be looking at method of what? Referring. Okay. Method of referring. It says there, transformer calculations are generally difficult because there are what? Two circuits. There are two circuits or windings to take into what? Account. Okay. These two circuits is the primary circuit and the secondary circuit. And these two circuits are isolated. They are not connected to each other. They are only just magnetically connected to each other. Okay. Method of referring. In order to simplify these calculations, we can match the what? The secondary winding with the primary winding. Or we can match the primary winding to the secondary winding. Basically, what does it mean, guys? We can take the secondary winding, primary winding. Basically, what we are referring to the primary winding. Or we can take the primary winding and refer it to the secondary winding. Okay. These meshed windings are called what? Equivalent windings, which has its own resistance, reactance, and impedance. Okay. Any value of resistance or reactance taken from one winding to the other is said to be what? Referred. Okay, let's turn to the next page. Okay. But they didn't show it, nah? Let me show you. They didn't show you the schematic. Let me draw you the schematic. What do we mean by this? Okay, this is our primary winding, guys. This is our primary winding. This is our secondary winding. Yeah? So this this winding is made up of and wire has what? Resistance. So This resistance R1 represents the resistance of the what? This winding. Nah? Okay. Then this represents the reactance or inductive reactance of what? This winding. Okay. We don't draw them here. Yeah. Why? For simple we are trying to be simple for simply. We don't want anything. We don't want to draw izoba clumsy kasinekudwa phi apha yonke. Instead, we represent it here in series with each other. Xa iyonke le nto ibizwa ngantoni? Okay, impedance ye-primary winding. Then beno R1, X2. Then this is the resistance, your resistance here, secondary winding, then your reactance is secondary winding. When we are referring, let's say we are referring the secondary winding, what we are basically doing, we are referring the secondary winding to the primary winding. So what we are basically doing is, okay, we are basically taking the resistance of this winding and put it on the primary side, the reactance of that winding and put it on the primary side. So we write it as prime. Yeah, but once you see prime, this comma there, that means we referred the resistance of the secondary winding to the primary winding, and we referred the reactance of the secondary winding to the primary winding. Now let us write down. Let us look at the formulas now. Looking at page 108. Okay. Niyabona equivalent resistance ibalwa njani? Basically, you add the resistance R1 and the resistance R2 referred to the what? Referred to the primary winding, né? Okay. And niyabona resistance referred to the primary winding is given by your secondary resistance referred to the primary winding is given by R and N1 N1 N2, because we are not always given this value, yeah, but we use the actual resistance and the transformer ratio. Okay, but if you notice, that's the referrer kwi secondary ane u-R1 yena uzothi you just basically do intoni reciprocal. Sorry. Also, guys, that's how we calculate equivalent resistance. That's how we calculate equivalent reactance. That's how we calculate equivalent impedance. And the left-hand side is when we are referring to the primary. The right side is when we are referring to we are referring the primary winding to the secondary winding. Okay. Now moving on, we're gonna look at a percentage or per unit values, ne? Then we quickly browse through a voltage regulation. Then we'll answer intoni September 2021. Guys, I'm trying to understand everything, yeah, so that you are able to apply your mind. As I've said that, but techniques wants you to apply your mind. Finally, physics, yes, high school. You don't just cram. Yeah, if you cram, it's over the mic. Yeah, over stuck. I'll send the question. Okay. Uh, guys, we're looking at a percentage resistance, percentage reactance, and percentage impedance. Okay. Why are we looking at this, guys? Is because the manufacturer of the transformer, the person who manufactures the transformer, give us these values in percentages or per unit values. Or per unit value ne, simply means if the percentage was 72%, or per unit value, you divide it by 100, is about 0, it's in a per unit value form. It's in a ratio form. Ne? Okay, that is what it means. Okay. Yeah. So, guys, there are two reasons why the manufacturer does this. Ne? The first reason, ne? Only if the impedance is given in percentage or per unit form, we can use the same value on either side to calculate the what? Equivalent resistance, reactance, and impedance in what? In ohms. So, guys, we can, if these values are given in percentage or per unit values, we can use either the primary side or what? The secondary side to calculate resistance, and only reactance and impedance. If you look at the formula there, the formula is the same. Let's say we wanted to calculate in only, we are given a per unit value of resistance. We want to calculate a equivalent resistance. I1, yeah, this is when we are referring to the what? Primary, because they are going to set an equivalent resistance here on a primary, over bani V1. Yeah, okay. If you wanted to calculate the equivalent resistance, you can still use the same per unit value on the secondary side. Yeah, to find no? It works, this value works on both primary and secondary. Yeah, that is why the manufacturer is giving us in percentage or per unit value form. Okay. Yeah, same goes with inwardly, reactance, impedance. Then, second reason, here is the second reason. To calculate the voltage drop due to a resistance, due to a reactance, we normally need to know a value of current. And a voltage drop, Ohm's law, I due to resistance, due to reactance. Yeah, but we normally need to know what is the current is, yeah, to calculate a voltage drop. But when if resistance and reactance are given in what percentage or per unit form, we don't need to know what the current. In answer stage, however, if we are given percentage or per unit impedance, we can calculate the voltage drop without current value. If you look at those formulas, let's say you wanted to calculate a voltage drop on the primary and on the a voltage drop due to a resistance, equivalent resistance on the primary side, referring to the primary side. So 30 per unit value, we multiply ngobani? V1. Yabo asidingi basazi ntoni? Current. Same goes for intoni? A voltage drop due to intoni? A reactance. Yabo. And yabona, this thing still applies in both what? The primary and the what? And secondary side. If we are referring the primary winding to the secondary winding. Okay. per unit V2. Yeah, still the same thing, nah? Sure. Okay. Then that's done, nah? Then lastly, let's look at a voltage regulation. I think I've just explained it. Nah? A voltage regulation, guys, we want a output a transformer to give us a constant voltage. Yeah, because if it output a transformer is negative voltage, yeah, we're gonna have problems with what with our electrical appliance. Yeah, okay. I-TV zethu zizothini zizotsha, yabo, because the voltage yeah too much, yabo, okay, or i-TV zethu azizusebenza because the voltage is what low. So that the transformer that is supplying maybe the street must give us a constant what voltage output. So it must give us a voltage regulation. Okay. Okay. Now we're gonna do a voltage regulation. Just indicate ukuba yintoni kancinci, then ndinibonise formula na. Ithi phana definition of voltage regulation of a transformer is defined as the rise or fall in the what? Guys, if voltage regulation only talks about a secondary voltage, talks about the rise and fall of secondary voltage. If you notice, when we look at a transformer at no load versus a transformer at load, you saw that a transformer at no load was equals to bani. But once we connected a load, we started to have internal what? Voltage drop, of which is E2 was no longer equals to bani V2. Right? So it was less. It's like a battery. A battery can measure voltage, open circuit voltage. You get a higher what? Voltage. But once you attach a battery, you connect it into a circuit where now you start having current that is flowing. You start having internal voltage drop in that battery. Yeah, hence the external voltage now it was slightly low because you have connected something. Okay, if voltage regulation is the rise or fall in the secondary voltage output when full load is what? Okay, provided the primary input what? Voltage remains what? Constant. Because remember, primary input voltage can also affect bani V2. Yeah, if we change the voltage in the primary, we will affect bani V2. But it's easier to maintain a voltage in the what? It is easy to maintain a voltage in the primary side. But it is not easy to maintain a voltage in the secondary side because it depends on the nature of the what? Of the load that is connected on the secondary side. Yeah, okay. Okay. Let us go to page 112. See that what you are E2 per unit regulation, E2 minus V2 new over bani E2. Guys, why why am I using E2? Because E2 kaloku is a no load what? Voltage, okay. Then V2 is the new voltage when we started to connect a what? A load. Yeah, Yeah, when this value is higher than that one, because when you start to connect a load, we get a voltage drop. Now, a low a percentage voltage regulation. Okay, okay. Basically, guys, uh, a transformer that has good voltage regulation. For a transformer, for us to say a transformer has good voltage regulation, maybe a percentage that is what? Uh, sorry, if let's say 240 minus 230 over 240. Okay, can I punch a calculator that? 240 minus 230 over 240 times 100. How many percent? 4,117%. You know? Times 100%. No? Okay. Let us say 240 minus 110. One. Time, times 100. Times 100. 54,97. Oh, sorry, 17. Okay, 17. Okay, thank you. Guys, you see that the higher the percentage your voltage regulation, that means the transformer has poor voltage what? Regulation. We don't want a voltage regulation a transformer a percentage high. Basically there is a threshold yabo. Okay, 240 minus 230. So basically if a transformer instead of bekumele sinike 240 if you go to that, that is not a bad situation. It means that if voltage regulation here is 4 point, but the higher the voltage regulation, that means we are getting low voltage at our output terminals, which is a problem. Okay, okay, and guys, let me explain this. V2 is not always what less than money. E2. You It depends on the nature of the what? A load. For example, UV2 can be greater than E2, maybe if we are talking of a capacitive load. I think I've seen that. Let us look at case one. The formula, guys, we're not gonna write it like this, obviously. Okay, this is a simplified formula. Formula that we're gonna use is for a lagging what? Lagging what? Power factor. Gonna use a voltage regulation per unit regulation would be I2 R2 power factor in the secondary, okay, plus X2 sine bani sine. Guys, the only values that we are using the secondary what values, because remember that's a voltage regulation. We are talking only in the secondary what circuit. Ngeke ubone I1 apha please. Yabo? Or yabo? I-voltage regulation, we are talking of voltage regulation on the secondary side of the transformer. Over B2 original. Okay. For that is for a lagging power factor. Ne? Let us go to the next page, 1114. Okay. For a lagging power factor, the voltage regulation is always what? Positive. Take note of that. Ne? The voltage regulation is always positive. The secondary terminal voltage will be less than the what? Secondary induced what? EMF. Okay, because of the voltage drop due to resistance and what? Reactance. Then lastly, you know, leading what? Power factor. Leading power factor. Leading power factor, and one more look at what we do there. We put in a what? A minus, né? Okay, still the same formula, né? Then if formula to calculate a voltage regulation using per unit percentage values. Nah? Let's say I wanted to find the percentage regulation. Okay. I was given a percentage what? Resistance, nah? And a percentage reactance. That is that formula in page 115. Anna? Okay. Then yambona umehluko ke when you're given intoni when when you're referring you have when you have calculated equivalent resistance ne equivalent reactance the last formula ne you have calculated equivalent resistance referred to the what secondary side the equivalent resistance referred to reactance sorry reactance referred to the secondary side. Those are the two formulas that we'll use. Okay, then we're done. I think we're done with the transformer. You can answer any question with understanding. Okay. In the ndifuna push after is those harmonics, then the missing neutral. Yeah. Then question one back to back test Hopkinson as a machine Z2. Okay. Because we done is swim banana. Okay. Let's go to the question paper. Okay. It says define what? Voltage regulation of a transformer. Name two effects of harmonic voltage in a transformer. Ne? Those are in the textbook. Ne? So let's look at question 3.3. It says there the percentage impedance referred to the what? Primary coil. Please write this. Referred to intoni primary. Okay. Of a what? 250 kVA. Ithe u-200 kVA yintoni guys? Yi-rating, ana? Transformers are rated in what? kVA. Ana? Why? Because iron losses, they are voltage dependent. Ana? And copper losses are current dependent. They are not phase dependent. I've explained it yesterday. So S is what? 250 kVA, which is the rating of the transformer. Ane? Then ke ngoku ithi we are given intoni 100 and what? 1800. Okay, sorry. 450. It's a single phase. Ane? Single phase transformer. Ne? Okay. What type of transformer is that? What type? True step down transformer. We have a what? A step down transformer. Okay. Then we are given a frequency, 50 hertz. Then we are given what? Impedance. Guys, I think the person who was writing this question, made a mistake. Emma, why do I say the person who was writing this question? And uthi phana ekuqaleni the percentage what? Impedance. Nansi percentage impedance. Sinikwe in what? In a unit called ohms. I-percentage values per unit values azina unit. So basically it was the error of that question paper. Yabo? So Tina will take it as okay, yeah, ayo percentage, impedance yamanyana. Yabo? I can even verify it for you in the textbook. Let's go to let's go to page page 109. None. Okay, sorry. Page 109. It in none of these resistance and reactance values are in what? Therefore, they cannot be used to calculate a voltage drops or in copper loss. These are not in ohms, but the guy who was setting here gave us this thing in ohms, but what he percentage impedance. That is not true. Remember? It's wrong. Remember? So we just assume okay, we're gonna work with the errata and assume that bangban ko ohms lo amphalile. Yabo? Okay. The power factor, anyway, power factor is 0.8 what? Nike. Okay, so qala ngo 3.3.1. Bafuna ntoni? The tens ratio. Okay, they want the tens ratio, which is V1 over bani? V2. Now V1 over V2, which is, okay, that was a giveaway. Okay, what is the tens ratio? 4 is to 1. Okay, then the next question wants us to find the percentage what? The percentage, sorry, percentage resistance. Okay. Okay. Okay, we want to find the percentage what? Resistance. Okay. Why I have referred to what? Primary side. That is why I was saying you must note the statement that says which winding are you referring to. Okay. So the formula that we're gonna use is layer per unit resistance. It's given by so sebenza le yentoni primary. I bani I1 R E bani over bani 1. But sifuna in percentage, not in per unit. So I'm gonna multiply by what? 100. Making sense, Now bayibalula njani? When you understand the techniques. Yeah. Okay. So I have indoni. I have indoni. A voltage. Yeah. I have indoni. E1. Yes. Oh, okay, fine. But what I don't have is indoni. Ubano RE1. 0.6. Because I log impedance. Impedance, a transformer, guys. You calculate it with indoni. Equivalent resistance and equivalent what? Reactance. Or calculate what high equivalent on your impedance R1 plus. That means you have been considered as a secondary circuit. Okay. Uh, okay. So we're only short of it only a current. Easy to calculate a current. Remember to tell a rating. This is a rating of a transformer. A rating of a transformer, you can use it with secondary, now with primary. So I'm gonna use it with primary. Where S is equals to V1 I1, which is 250 V1 bani. Okay. What is my I1? 1 138 comma 8 9. So kanene times 10 to the power what? 3. 10 cool and none. Okay. We have calculated I1. Now we can calculate the percentage what? Resistance. Uh, 0.6 1800 times 100. What is the percentage resistance? 4.63%. Okay. The next question is the percentage reactance. Okay. 3.3 point. Uh, 3 point. Okay, this one was 3.3.2. This one is 3.3.3. So a percentage reactance would be I1 U1, which is 4.4 1800. What is times 100? What is the percentage reactance? Equals to 33.95%. The next question is full load copper loss, guys. Casifuni copper losses. Short circuit test, is equals to bani. Straightforward, bani ke follow sorry 11,58 kilowatts. Okay, then next one, sorry, next one, again ayifani mfakelo squared, huh? Squared, then ngu 0,6. Okay, then 89 question. Okay, guys, this one is not in your textbook. Please write it down. Power factor at what? Maximum what? Reg. Anna? So write it down. Power factor is equals to cos R over 1 Z E. Power factor at maximum regulation. Okay. Cos theta 2 to show that by it's at maximum regulation. R over ZE. Okay, RE, sorry, RE over ZE. Sorry. Yeah. What ZE is basically nangana, but kalanin convectile to a polar sizofumana the absolute value of ZE. Nathi. Sorry? Ile impedance le. Kala ninenzela ibekwe ibekwe polar 4, 44, 4, 441 82, 235. Okay. Okay. We don't worry about the angle, né? Because the power factor is a ratio, and a unit, né? So cos power factor it is over bani. OR bani go 0,6 over 4,44. One power factor. 0,135. Is it leading or lagging? If you look at OZ ngubani? Intoni? Reactance. What type of reactance? Inductive reactance. So akasine inductive reactance intoni? Lagging. If we minus, then we know we have intoni? Capacitor pha. So it is about leading power factor. Make sense, nah? Then you can use what angle you can use? This one. you know, the this angle. Kawusebenzisa the method kabani ka cos, remember nje it's cos bani, ne? Kawusebenzisa cos, you use the angle of intoni impedance, which is 82,235. Term panje jonga bazofumana day 1. Okay. Then the last question, which is 3.3.4. Is it 0.5? 0.5. If we're not done. Okay, they want the applied voltage to the primary to circulate what? Full load current in the secondary. That is basically short circuit test. Can you please turn to page? What page is this kind of short circuit test? Because we use a short circuit test to circulate full load current in order for us to determine the full load copper loss of the transformer. Okay, can you please turn to page 122? Oh, the short one is what? The short one is okay. Okay, do you get it, guys? In order, if guys went up yesterday, for us to circulate a full load current, we connect a short circuit in the secondary side. Then gradually increase the applied voltage until kuthini? For a full load current. You remember yesterday, na? Yeah. So that is why I'm using a short circuit test to find the applied voltage to circulate in full load current. That A1 bani ku 4 comma sorry 4 comma 4 4. Ito lang bani yung short circuit voltage ito. Am I forgetting something? Okay. Wala bang ba? 616 comma 67 volts. Okay, guys, that's basically it for question 3. We can go through the memo. Long into sharp, ne? Okay. Let us take a short break.